Hi, it's time for another math easy solution. To discuss further into Euclidean division and now look at Euclidean division for polynomials and go over the theorem and proof. It's going to be a pretty extensive video, so if you don't have time to watch the whole video, you can play this video at a different speed like always. And that's my top secret life hack. Try 2x speed on YouTube. It's quite amazing. Anyways, let's just jump right in and look at Euclidean division for polynomials, theorem and proof. But before I get to that, let's just look at or recall from my last video on Euclidean division for integers, where I showed that the division a over b, for example, if you had something like 9 divided by 2 as integers, this could be written as, well, you could just break it up in your head like this. 8 plus 1 is 9 divided by 2. This breaks it up into 4 plus 1/2. And then you can rearrange this, multiply by 2 on both sides. So what we end up getting is 9 equals to a 2 times 4, and then the 1/2 times 2 is just 1, like that. And then basically what this means is, and more generally what we have is, if you have a divided by b, where b is non-zero, then what we have is a is equal to b, the divisor, a is a dividend, times it by q, which is the quotient, which is 4 in this case, and then we have plus r, which is the remainder, in this case is 1, and this is with 0 is less than or equal to r, and r is positive, and it's less than the absolute value of b right here. So yeah, this 1 has to be, well, the remainder here has to be less than the 2 there, or the absolute value of it, because then it means it doesn't divide it out evenly. Or in other words, it's just a fraction of 2, like that, which is the remainder here divided by the divisor, and there's the remainder r. And we can just circle this out right here. So this is what we get when we divide it, and this is again, q and r are unique integers, as I explained in my earlier video, so make sure to watch that. I'll put that in a link in the description below. So these are unique integers. And also we have b is not equal to 0, so we don't have a divided by 0, which is undefined, like here, undefined. Yeah, so now that I've gone over the recap of it, just to show you how it's pretty much very similar to the polynomials one. So now in this video I'll be looking at Euclidean division for polynomials as opposed to just integers. And now recall that a polynomial, or more specifically a univariate polynomial, which consists of just one variable, is of the form, and just to get a recap on polynomials, this is going to be of the form p of x like this, and this equals to a0 x0, and this is just a coefficient or a constant, and this is x power of 0. In that case, that's just 1, plus a1 x1 plus a2 x2, and plus keeps going on and on until finally we have an xn, like that. Yeah, so this is a polynomial of one variable, or a univariate, or a single variable polynomial. And I'll write where, so where we have the values a, I'll write ai, indicating it could be any one of these, 0 all the way to n. So ai, this is just a constant right here. These are just constants, like that, or constants. And we also have xi, x to the power of I, where we have basically I is equal to positive integers, like this, positive integers over here. So 0, 1, 2, 3 all the way to there, so it's positive integers. Otherwise, if it's a negative one, we don't get a polynomial. And also now what I'm going to do is note, for the cases of this video, I'm going to call something as the leading coefficient. LC equals leading coefficient, like this, coefficient. And I'm going to define this as basically a n there, which is equal to the coefficient of the highest degree of variable, like that, or a highest degree, the highest power there, x to the n, which is going to be the highest one as you increase, like that. And I'll just write this as a function for this specific polynomial. So LC of p is equal to a n. This is our LC, like that. And also the degree, so I'll write n is equal to the degree of the polynomial. Yeah, so then this is the degree, like that, degree, or the highest power of it. And again, write this as a function. I'll write this as degree d e g, and function of the polynomial p is equal to n, like that. Alright, so now that we have these definitions out and the polynomial, just to recap on that, and now when we go into the Wikipedia's one as a definition and the algorithm that we're expected to prove, and it goes over the Euclidean division polynomial. So let's just go over it, and then I'll go over the derivation and proof. So basically, if Wikipedia has polynomial greatest common divisor, in the subsection of that has the Euclidean division for polynomials, which is used in Euclid's algorithm for computing GCDs, its greatest common divisors. I might go over those in later videos, but for now that's just outside the scope of this video. So it's very similar to Euclidean division for integers, as I explained above. Its existence is based on the following theorem: given two univariate polynomials, so polynomials with one variable, a and b is not equal to 0. In other words, we don't have a over so a over b is not equal to a over 0. So we can't divide by 0 like that, because it will just be undefined, as I explained above. So it's defined over a field. There exists, so if we have two polynomials a and b, there exists two polynomials, q the quotient and r the remainder, which satisfy this formula like here, and looks very similar to the integer ones. It's exact same, but these are now polynomials. A equals b times q plus r. A is the dividend, b is the divisor, and q is a quotient, r is the remainder. And then the degree of r is less than the degree of b, meaning the highest power of r is less than the highest power of b, where this right here denotes the degree, and the degree of 0 is defined as negative. And this is actually in case, and I'll explain this even further, in case the degree of b is equal to 0. In this case, what we actually end up having is that the remainder here, in this case, if the degree is 0, we're just dividing by a number, and then the degree, or r of x, will just equal to 0 here, and the degree of 0 is going to be defined as negative, and this will make sense, so that it's negative is less than the degree of b, and we will go further, and this will make more sense as I get in later in this video. So moreover, q and r are uniquely defined by these relations. And now the difference from Euclidean division of the integers is that for the integers, the degree is replaced by the absolute value of the divisor, as explained, or b, and that to have uniqueness, one has to suppose that r is non-negative. So and even in this case, we're dealing with r as non-negative. Actually, I mean, that was for the other one. For integers, you assume it's non-negative. For here, all we worry about is the degree. So you could have some negative values, and that doesn't matter. So that's just a difference there. So absolute value, and then we have r is non-negative. So the rings for which such a theorem exists are called Euclidean domains, and that's outside the scope. I might go into that later. So like for the integers, the Euclidean division of the polynomials may be computed by the long division algorithm, and you can learn more about long division about polynomials and integers or numbers in my earlier video. Put that in a link in the description below. So this algorithm is usually presented for paper and pencil computation, but it works well on computers. One formalized as follows: note that the names of the variables correspond exactly to the regions of the paper sheet in a pencil and paper computation of long division. It's pretty much long division. In the following computation, the degree dig stands for the degree of its argument, with the convention degree 0 is less than 0. So degree of the function 0, that is just r of x equals to 0. And again, they have LC, L is lowercase, stands for the leading coefficient, as explained above, which is just the coefficient of the highest degree of the variable. And here is what they have written here. And this is Euclidean division. There's that algorithm here. It says input a and b is not equal to 0, two polynomials in a variable x. Output q, the quotient, r the remainder. And it has a function here, begin q is 0, r is a, then d is degree here. You're just defining these. And then it says while the degree of r is greater than degree of b, like here, this is while this is true, so it's not less than it, do this, then has an s value, and I'll explain why they have it like this. They've chosen the leading coefficient of r divided by leading coefficient of c, leading coefficient of b over there, times by x, then degree of r minus degree of this is d, degree of b over there. Then they've added s to the q, and it keeps going on and keeps repeating. And I'll explain this in a step-by-step method just to illustrate it, prove it, and show that it works, and to explain what it does in a bit. But first, now let's read further. So the proof of the validity of this algorithm relies on the fact that during the whole while loop, we have a equals b cubed plus r, and degrees r is a non-negative integer that decreases. Yeah, so the degree of it keeps decreasing at each iteration, and then you basically stop once you have a degree of r is less than the degree of b, and thus proving the theorem. So that's always valid, and is just keep going. So thus the proof of the validity of this algorithm is also proves the validity of Euclidean division. So now let's prove that this algorithm works, and hence prove Euclidean division. Yes, so to make sense of all of this, what I'll do first is, well, I'll write the input is, so we are inputting a over b, where we have b is not equal to 0. So these are two polynomials, and also both are functions of x, like here, of x. So these are both polynomials of x. I'll put this in bracket, polynomials, like that. And now what we'll do is write the theorem out. So the theorem is just a Euclidean division. A equals to b q plus r. And now where each of these polynomials, we're going to write these as, and I'll write where these are all polynomials. And now what I'll do is I'll use the leading coefficient method, and I'll write this as where a of x is a polynomial, and I'll write this out. So if we go back to the polynomial, the form of it like this, what I'm going to do is I'm going to write this L of c in front, and then these ones, they don't matter much, and I'll explain why. So I'll just write this as the leading coefficient of a times it by x to the power of the degree of a, like this. Remember, that's just n, this is just a n, like this. This is just a n, this is just n. Yeah, so that's just n, like that. And then I'm going to do is plus dot 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 is just the rest of the entire one. It could be a0, a1, and so on, but I just move this in front. And then same with the b of x, the divisor. This equals to LC of b, the leading coefficient of it, times x to the degree of b. And then likewise, we're going to have dot 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 plus dot dot dot, and so on. And then now what we have here is c of, not c, this is q. So the quotient q is also going to be written like it. The leading has a leading coefficient, has x to the degree of q, or the highest power, like this, and then plus dot dot dot. Dot, dot, dot. This will make more sense as we get further. And now the R1, the remainder, is going to be in a similar way, L of c of r, x degree of r, plus dot dot dot, plus dot dot dot, and so on. And now, before I get to the algorithm, but first let's just look at an example of long division to illustrate it, and then later, once I prove the algorithm, I'll be basically revisiting the same example and do it using the long division, the Euclidean division algorithm. So for long division, let's say we had a function x plus 3 squared as polynomial divided by, and now we have 2x plus 2. So this one, first we could just expand this, write this in the form we are used to, just expand it as the p of x form as above. So to multiply this out, this will be x times x is x squared, plus x times 3 is 3x, and then plus 3 times x, that's 3x again, so we can add them up, 6x, and then 3 times 3 is 9, just using the FOIL method, and then the middle part is in my head. So we have like this, and then divided by 2x plus 2. Yeah, so in other words, this is our a, let's write this as a, divided by b is the polynomial, the divisor, that's a dividend. And now using long division, so long division right here, just to illustrate it, and I'll put this L. So what we end up having is a division like this, 2x plus 2, and then put this above x squared plus 6x, and then plus 9. And you can learn more again about long division. I'll put the video in the description below for my earlier video. So now what we have here, what we do is, remember the method is we need to multiply a variable here to get this 2x, and what we'll do is, well, that's just going to be x. Actually, no, other way around. We need to get the x squared, my bad. So we need to cancel the x squared, and what we'll do is multiply this 2x by, well, 1/2 x. So when we do that, what we get is an x squared, and then this one by this, the 2's cancel again, we'll just be left with plus x, like that. Then we can just subtract, and when you subtract, this cancels, now we have this 6x minus x, that's just 5x. Carry the 9 down, we have plus 9 like this. And now what we have over here, we need to get the 5x, so we multiply over here by plus 5, well, over 2x. Actually, no, just leave that x out. So 5 over 2. So 5 over 2 times 2x, that just becomes, well, the 2's cancel, that's just 5x. So we have 5x, and then over here the 2's cancel again, that's just plus 5. Like that. Subtract. This cancels, now we have 9 minus 5 is 4. And now we can't get any further to this one, so that's the remainder. So this is r, I'll just write this as r of x, like that. And now this whole thing on the top is the quotient, q of x. Yeah, so thus what we have written in the Euclidean division form. So thus, well, before we get to that, yes, we have over there the whole thing. So let's put this over. So we have x squared plus 6x plus 9. I'll just write thus here. So thus, x squared plus 9, all divided by 2x plus 2 equals to the quotient 1/2 x plus 5 over 2, and then plus the remainder 4. In other words, then when we multiply this on both sides, actually, yeah, this is the fraction, plus 4, and it can't divide evenly, so we just leave it out there, and it's just 4 divided by 2x plus 2. Remember, that is the long division method. Now when you multiply by 2x plus 2 on both sides, we can cancel that. What we end up getting is an x squared plus 6x plus 9 equals to, now let's put this in front, 2x plus 2, and then we have this 1/2 x plus 5 over 2, and now we have plus the 4, so the 2x plus 2 cancels out like that. Yeah, so in other words, here we have our a equals to, here's b, and here is the q, and there's the r, like that. And thus what we end up having is, I'll put this out like this, each of the functions. So a of x, just to make it like the other one, a of x equals x squared plus 6x plus 9, and in this case we have the leading coefficient is going to be, well, just 1. Leading coefficient of a equals 1, and the degree here is 2. Degree of a equals to 2. Likewise for our b of x, that just equals to our 2x plus 2, 2x plus 2, and then the leading coefficient of b is going to be equal to 2. So that's the leading coefficient, and then the degree of b equals to 2, like that. Yeah, I mean, the degree of, yeah, my bad. The degree of b is 1, because that's the power of 1 over there. Likewise for the q of x equals to, that's 1/2 x plus 5 over 2. Now the degree, or the leading coefficient, is going to be 1/2. And then the degree of it is just, that's going to be 1 as well, again. Equals 1. And then last one is the remainder, is just, remainder r of x is just equal to, yeah, the remainder is just going to be equal to 4. Over there, that's just 4. So then the leading coefficient, again, you could think of it as x to the power of 0. Leading coefficient is just 4. That's the highest power there is the 0. This is going to be equal to 4, and then the degree of r equals to 0. And also notice, note that the degree of r is less than the degree of b. Yeah, the degree of r equals to 0, which is less than the degree of b, which equals to 1. So yeah, this fits our Euclidean division. And now to prove that algorithm, just to give you an example of how to define all these terms, just to illustrate it further. And then later I'm going to show the Euclidean division is the exact same thing as the long division that we just did over here. Yeah, so thus what we have is, let's just go over our polynomial long division, or polynomial division algorithm, like this. Yeah, algorithm. And then this will prove the Euclidean theorem there. So what we have first is we always have A equals to B, Q plus R is our theorem we always need to have. And now what I'll do is I'll make a giant table like this, and I'll write this as the first column is just going to be the row number like that, and put it out somewhere over there. I'm going to call this one 1, so row 1. Then we have our Q values, and remember as above in that giant table, and I'll just be going through it. It's pretty straightforward when you go through it. So initially Q is 0, R is A there. So we go back. So this one needs to always be satisfied. So put that in a box. So Q initially we have Q1 equals to 0. And then the next step would be, well, choose our R. So R, you can just rearrange it. So R needs to ensure that this theorem is true always. So A minus BQ, like that. Yes, we have this part here. And then what we have is, well, R1. And plug in Q1 inside, that's just 0. So we have R1 is equal to A, as the input did in the Wikipedia statement. And then the next column here is we check if the degree of R is less than the degree of B right here. Is it? And put a question mark over there, extend this further. So then I'll write if yes, it is, then we're done. Yeah, so if yes, we are, if yes equals to done, and we just put that done. Yes, if it is less somehow, yeah, then it is just done. And then if no, we continue. So if it is, then that's all good and dandy. So no, yeah, if no, actually, before what I mean by continue, we add S. This is what I'll write S1 to Q1. And then I'll explain how the Wikipedia page determines the S1 there. And the reason is we got to increment it until this one keeps going down and down. So then now we have the second row over here. Row number 2, we have Q2 equals to, well, Q1 plus the S1, a new value. And then that's Q1 is 0, so that's just equals to S1. So then this equals here. R2 is going to be equal to, we'll plug this inside. So we have A minus BS1. A is just this over there. So this just equals to R1 minus BS1. Yeah, so now that we have this subtraction, and now what we have here is, well, we need to make sure the degree of R is less than the degree of B, but we want to ensure we want to ensure that the degree of R2, so the new R, degree of the remainder 2, is less than the degree of remainder R1, so that it's always decreasing. So eventually we'll get to less than degree of B. And then the question is, how do we do this? And that is by choosing the value of S1 very specially or specifically to get it. Let's put this a bit better like that. And now what we'll do is I'll just move this down. So cancel this, let's put this down. How do we do that? So what I'll do is I'll write notice first what we have, and that thing that we need to worry about is this R1 minus BS1. So R2 equals to R1 minus BS1, or more generally, I'll write more generally. So yeah, basically, more generally we'll have it as writing, instead of 1, I'll put that as I. So, and then instead of 2, I'll write I plus 1 equals to RI minus BSI, so the previous one, like that. So more generally, we have this over there. And now what we could do is write this in the leading coefficient way. So what we'll have is RI plus 1 instead of R2, and just write RI plus 1 more general. And then what we have, because we want it for every single term to lower, and now what we have is this one here, the RI. I'm going to write this as leading coefficient of RI, because remember, it's just a polynomial, times it by x to the power of degree of RI, and then it has plus dot dot dot, random stuff like that, the other terms that I don't really care about because I want to lower the degree of it by 1, so we just put the highest degree there. And now we subtract it by b, which is going to be leading coefficient of b times by x to the degree of b plus dot 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 plus dot dot, and we keep going on and on. And then lastly, the SI, it's still going to be a polynomial because we'll be adding it to the Q, so we need it to be a polynomial. So multiply the B1 by, this is going to be now LC of SI, leading coefficient of it, times by x to the degree of SI, like that, and then plus dot dot dot. But I'll show you this eventually becomes, those are just, we could just remove all those terms because all we need to worry about is lower it by 1. By 1 degree, so all we need to actually care about is this leading coefficient. But this will make sense in a bit. So let's just multiply this out so to see what we get. So this equals 2, just write this back down again, LCRI, it's the leading coefficient of RI, x to the degree of RI, plus dot dot dot, keeps going on, and then minus, now multiply this inside. So the highest degree that we're going to get is going to be when this multiplies by this. Every other one that you multiply, you're going to be multiplying by like the B1 or the highest degree by a lower degree, so those don't matter too much. Then what we have is an LC leading coefficient of B times by leading coefficient of SI times it by now x, and now these just add up. Just like how when we multiplied the x plus 3, we had x times x is x squared because those degrees add up. So now we have an x degree of B plus degree of SI, and then we have a bunch of other terms that multiply out, but they all have a lesser degree. Just put like that. Yeah, so now what we have is, well, we have a subtraction here, and we have a highest degree over here of RI, but what we want is we want this whole thing, and this one over here, the highest degree of this term here, we want these to both cancel. Like that. I'll just put this over there. Want to cancel these. Yeah, so we want to cancel, and the reason is, yeah, and then this is the reason is so that this degree of RI vanishes, and then we want to cancel so that degree of RI plus 1 is less than the degree of RI. So we've removed the highest degree there. Yeah, so we want them to cancel, and in order to do that, we'll just make it basically equal each other. So this is number RI plus 1. Thus, the only way it's possible, if they equal each other, that's the only way we're going to cancel. LC of RI, the leading coefficient of it, times degree, x to the power of degree of RI, like this. And then, again, you have the plus plus. Actually, we don't even need the plus plus because we just need to cancel these ones here. These ones just need to be equal to each other. So this has to equal to this on the other side, LC of B, and then times by LC of SI, and then times by x to the degree of B plus the degree of SI, like that. And this is only true if these are equal to each other. So then we have these equal, so we have LCRI equals to LC of B times LC of SI. And again, you could just rearrange this for the LC of SI is the one we want to find out because we're adding it to the Q. So LC of SI, leading coefficient of it is going to be equal to, just move this over, so we get LCRI divided by LC of B, leading coefficient of it, and this is exactly what is used in the Wikipedia algorithm. And likewise, these degrees need to equal each other. So then, and also what we need is, well, x degree of RI equals to x degree of B plus degree of SI, like that. So then we have over here, these equal each other, degree, yeah, so then the degree of RI equals to the degree of B plus degree of SI, like that. And then we could just rearrange this one, and we get degree of, yeah, so then the degree of SI equals 2, and now what we have over there, just move this over to this side, and we get degree of RI minus the degree of B. Very, very interesting. And it's exactly the same thing as the Wikipedia algorithm. Yeah, so thus what we have is, alright, thus we choose, so we choose our SI, choose SI equals to, this one here is just going to be, just put the leading coefficient of it, SI, times it by x to the degree of SI. And then we have plus dot dot dot, plus dot dot. This one, all we need to worry about is, well, is just to get rid of this leading coefficient, or just this whole term there. So all we need to worry about is this. So what we could do is we just need to choose any of them, and also write this as, choose this whole term as 0. Choose 0. So make it just basically nothing there. So then what we have is SI, and we replace this by the value that we want is over here. So we want LC of RI equals to, LC of SI equals to this, the difference. So we have SI is equal to LC of RI divided by leading coefficient of B times it by x to the degree. And now we have this one over here. So we have x to the degree of SI, which is degree of SI is just the difference RI minus B. So x degree of RI minus the degree of B, like this. And then we just choose the other part, all equals 0. So then this one right here and this over here, this is what we choose, and this ensures, it ensures that the degree of RI plus 1, so the one after, is going to be less than the degree of RI, like that. And it's absolutely genius, actually. This is hashtag genius, actually, when we work it through. So if we go back up, notice this one, the difference of the RI and B and the leading coefficients, and then the subtraction of that. So you have the division there, just to show you it's exactly the same one, and that's why they chose S in such a way. So if you go here, they chose leading coefficient of R divided by leading coefficient of the C is the B one, then degree of R minus, and then degree of B there, and it's exactly the same thing here. And it's the while, this one they have it, if it's greater than it, keep doing this, and so on. I just have it, if it's less, stop. The same thing. And this is exactly the same one. It's absolutely genius algorithm there. And then that is what our SI is, and that's when we have R2 less than R1, and so forth. You keep going on until it's less and less and less. Yeah, so now let's revisit the Euclidean polynomial or polynomial algorithm. So revisiting, and put that all together, revisiting the Euclidean Division Algorithm for polynomials, like this. Let's just revisit it. Like, let's put a better underline like this, underline, and go on. Yeah, so like always, we have our theorem A equals to BQ plus R needs to be valid at all times to ensure that, our theorem works properly. And thus we do, let's just start it again. I'll put this as the question, the number of the row. So we write row 1, we have initially Q like this. Now we have here Q1 equals to 0. Then going further now, so that's initially there, then our R, just move that over, R equals to A minus B. Q, like this, and then we plug in our Q1 is 0 in there, R is equal to, R1 equals to A. And now the question remains over here, and I'll write degree of R, is it less than the degree of B? Like this. So that's the question. If yes, equals stop, and then no equals continue. Let's put no, yes equals stop, no equals to continue, and we just add the SI to it. So we continue here. Number 2 is going to be, well, Q1 plus SI, so Q2 equals to Q1 plus S1, which just equals Q1 0, like that. This just equals to S1, like that. And then R2, remember as above, R2 is just going to be, we'll plug in S1 in there, equals to A minus B S1, and then this A is just over there, equals to R1 minus B S1, and then these subtract, and then we remove the highest power, and here, now that we have this one, and then here, as I showed before, the degree of R2 is, well, less than the the degree of R1, and then so on. Now we just check if it's less than B. If it's yes, we stop. If it's no, we continue. So dot dot dot. And this one here, that S1, the way we chose it, we always ensure that the next R value or next remainder always less degree than the other one, and eventually it'll be less than B. Then now next step here, we have Q3 equals to, well, we just add another S value. So we have S1 there plus S2. So it's the second one based on the previous value there. So then we have R3 now. This equals to, we can just plug that in, A minus B times Q, which is S1 plus S2. Just to show you what we get. A is our value there. So this one just going to be A minus BS1 plus or minus BS2. So this BS1, this is just our R2. This just equals to R2 minus BS2. So we always subtract. So then the R3, like here, it's always going to be the previous R minus the B times S, and then the S2, like that, or the previous one, like that. And then here as well, we have degree of R3 is less than degree of R2, and so on. Now we just keep this method all the way until we get to K. So here the kth row, we have now Q of K is going to be equal to S1 plus S2. It's always one less, so plus dot dot dot, and then we get eventually SK minus 1, so the previous one there. And likewise here, this goes all the way down here until we get R of K, which is going to equal to RK minus 1, and then minus BSK minus 1, like that over there. And then this is the kth one is eventually here, because we're always decreasing. Eventually degree of RK is less than the degree of B, and then basically we've proven the algorithm. Yeah, and basically we have all the way down here, these are all, I'll put this all like this, decreasing. I'll put it actually over here, put dot dot dot, and just put an arrow like this, decreasing degree of R like this, or Ri. So it keeps getting less and less, and eventually just less than the B over there. So then thus this proves, and I'll write thus this algorithm is valid. Algorithm is valid, and since it's valid, the theorem above has been held, it's been basically taken into account the entire time, and the degree is always getting less and less, which will eventually get less than B. So thus this algorithm is valid, and thus the Euclidean division, so the EU for polynomials, or the theorem is correct. Euclidean division theorem is proved. So because we proved this algorithm, thus it's proved. Hashtag amazing. This is actually quite an interesting proof, where we prove it by proving the algorithm instead of just a conventional proof type method like that, and over there. And then again, note, as the Wikipedia does, note it defines over here, define degree of 0 as less than 0, and this is in case of, or in case when the degree of B is equal to 0. In case when degree of B is equal to 0. And an example of this is, i.e., if we had something like, let's say we had 9x polynomial divided by another polynomial 3, that's still a polynomial, this equals to our A over B, and then if you just divide it out, that just equals to 3x over there. Now if you multiply both sides by 3 on there, what we end up getting is 9x. Well, this equals to 3 times it by 3x. And then we'll have a remainder plus 0. That's going to be, so then we have A equals to B is a divisor, times it by Q is a quotient, plus R here. So then what we have is R is equal to 0. So we have R of X equals to 0, and the degree of B is equal to 0 right here, because that's just degree of x 0. Yeah, that's just 3. It's just a constant. So then we have to define, for the algorithm purposes, to keep it going, thus define degree of 0 is less than 0, which equals to the degree of b in this case. So that's why we have that case there, just make it less, even though technically they're the same degree, because they're both constant. 0 is still a constant. So now, just to illustrate all this, let's go revisit that same example of that one above. So let's use that same long division one, but now we're going to deal with the Euclidean division. So x plus 3 squared. Now we have the 2x plus 2. This equals to, again, expand that, x squared plus this 3 times x plus x times 3 is going to be 6x plus 9 as above, like that. Put this better. And then divide this all out by 2x plus 2 over there. And then this, again, this equals our a over b, like that. And we always need to have a equals to bq plus r. So that's the Euclidean division. Now what we'll do is make the giant table like this. Put row number here, and I'll write row number 1. And then we have our q value here, q1 equals to 0. And then the next one we're going to do is, well, we need to determine our r value. So r, just move this over, equals to a minus bq. So r initially is going to be r1 equals to a right here. Or I'll write this out like this. r1 equals to a, and a is just the top one there, equals x squared plus 6x plus 9, like that. And now the degree, now we do the check, is the degree of r less than the degree of b, like this. And in this case here, the degree of b is 1. That's just 1, which equals to 1. Is it? And this is the question. So then we check here, degree of, well, r here, degree of r1 equals to 2, which is greater than 1. So we do no right here. So now we have to choose our S1 value. S1 is going to equal to, remember, the leading coefficient of R1. So LC of R1 divided by LC of B times it by X, and then the degree of R1 minus the degree of B, like that. And then now if we write those out, LC, this is going to be, well, 1 there. So if 1, then degree, the leading coefficient of B is 2. That is LC of B, that's 2. And then X, then the degree of R1 is 2. So we have 2 minus degree of B is just 1, like that. This just equals to 1/2 of X. So that's our S1. So then now we have that part set up, and I'll just write this out like this, and then expand this out, and now we have Q, that's Q1. Now the second row, I'll write this as number 2 over here, and then the Q2, we add S1 to it. This equals to just S1, and this equals to, over here, this is going to be plus, that's just S1, which equals to 1/2 X, like that. Or I'll write the Q1 plus S1 just for completeness, and this is 0, this is just going to be 1/2 of X, like that. And then we subtract it. So now we have R2 is going to be equal to R1 minus, now we have B S1, like that. Again, you can plug in those values there and you'll get the same thing. And then the S1, so R1, I'll put this all, actually before I do that, I'm just going to expand this out. So B is just 2X plus 2, and then S1 is 1/2 of X. So when you multiply that inside, what we end up getting is, well, we equals to R1, or actually I'll just write the R1 first. So this equals to R1 is the X squared, that's just above here, plus 6X plus 9. And then now we have here minus 2X times 1/2 X. The 2's cancel, we just have minus X squared. And then here again, minus 2 times X over 2, the 2's cancel, minus X like that. Notice what we have here. This cancels with this, and then this one, and here we add up those up. This is equals to 5x plus 9, like that. Exactly as long division, where we had 5x, 6x minus x is 5x, and we carry the 9 down. We have 5x plus 9. And now we check again. Is the degree of R2 equals to 1? Equals to 1, which equals to degree of, this is going to be b, like that. So it's not less than it equals to it. So thus we do a new s value. So s2 is going to be equal to the leading coefficient. Yeah, so the leading coefficient of this is 5, divided by leading coefficient of b is always going to be 2. And then we have now x. Now the degree of R2 is 1, minus the degree of this one is 1. So we get 5 over 2x 0, or just equals to 5 over 2. So that's what our S2 value is. So that's what we have when we move over here. Expand this out. We get the third one here, or I'll put it over here, 3. Q3 equals to, well, it's always going to be Q2 plus our S2, which equals to 1/2 x plus S2 is 5 over 2. And then we just add that over here. So R3 equals to R2 minus BS2, which equals to, again, R2 minus, now we have 2x plus 2, and then we have this 5 over 2x over there. That's the S2 value. And then what we do, this R2 is just equal to 5x plus 9. Multiply this out. The 2's cancel. We get minus 5x. So again, so we can cancel these out like that. Then we have this minus 2's cancel there. So we have minus 5. Yeah, this is an x. Yeah, I forgot this is an extra x there. Yeah, so mistake there. So we remove that x over there. Yeah, so 5 over 2. Then there's still 5x there. And this one, negative 2 times 5 over 2. The 2's cancel, negative 5. So this cancels. Now what we're left with 9 minus 5 is equal to 4. And that is our remainder. So now the question is, the degree of R3 equals to, well, 0. That's just 4. So that's equals to, and this is less than 1, which is the degree of B. So what we do now is, well, we stop. And that is our remainder. So R3 is the remainder. And then what we have is, thus, we have two values. Q3 equals to 1/2 x plus 5 over 2. And R3 equals to 4 is the remainder. Yeah, and thus what we have is the overall one, A over B. Yeah, which equals to our x squared plus 6x plus 9 over, like this, over the b 2x plus 2. In long division, this just equals to now our Q3, which is 1/2 x plus 5 over 2, and then plus the remainder over there, which is just the 4 divided by 2x plus 2 as a fraction, like that. Yeah, so that's our A over B. This is our Q, and this is our R over B. In other words, put that in the Euclidean division one. We have x squared plus 6x plus 9 equals to 1/2 x plus 5 over 2. Move this over. That's our Q. Times it by 2x plus 2, and then multiplied like that, plus 4 as a remainder. So there is our Euclidean division like that, for example, and it's exactly the same thing. You can just divide it out or multiply it out like that, and then you get it in this form like that. Absolutely amazing stuff like that. I'll move this down and circle this answer. And it's exactly the same answer we did using the long division, which is, this is actually the long division method proof for it as well. And now just to summarize all this, a summary, just wanted to do the example in this video just to illustrate it all better. Summary for A over B division, or you could write it as A slash B, or A divided by B, or we have it as this method, or this long division, B over A, and B are basically univariant or single variable. All right, single variable, or yeah, this is basically univariant. You could write it as that, or univariate polynomials, and then with b is not equal to 0, so you can't have that. Then what we have is the Euclidean division a equals to b q plus r, like this, with degree of r is less than the degree of b, so we're going to have eventually one like that over there. And if degree of r is actually not degree of r, and if r equals to 0, yeah, so if r is equal to 0, assume a degree of 0 is less than 0, and that is yeah, just assume it's negative, and that's for algorithm purposes if we have the case where b is degree of b is 0. And yeah, this is summary of Euclidean division for polynomials. Euclidean division, just put it all completeness sake. So if you've seen this this whole video with a couple more minutes, doesn't help. That's not gonna do too much. So Euclidean division for polynomials, like that. And yeah, that is all for today. Keep going further, like this. Yeah, so that's all for today. Hope you follow along. It's pretty extensive video, but if you watch the whole thing, it's you're pretty much an expert in Euclidean division. Because I like to do it, even if it's long, as long as you know it full well, and it'll help you later in other math and division and algebra and so on. It was all for today. If you follow this pretty extensive one, and basically we've just proven this algorithm works and made sense of this random computer code Wikipedia put, and yeah, so it proves that there are q and r such that r is always going to be less than the b, and that theorem holds true. A equals b q plus r. It was all for today. If you learned, like always, you can download these exact notes in the link in the description below, video description. Also, make sure to watch or review all these notes in article format on Steemit, so follow me at MES. Also, make sure to check out my math and science forums, or just go and post some cool math or science related stuff you find. And it was all for today. Thanks for watching, and stay tuned for another Math Easy solution.